ओके, कल जो हमने किया था हम वहीं से शुरू करेंगे. ओके, लेट मी शेयर स्क्रीन. व्हाइट बोर्ड वेटिंग रूम में कौन है? ओके, इसको जरा मिनिमाइज करते हैं. इसको मैक्सिमाइज. आई थिंक देयर इज. ओके. ओके, तो जरा इसको साइड पे करता हूं मैं. सो फार हमने देखा वो जो डिफरेंट मोड्स ऑफ कन्वर्जेंस है, एक नॉर्मल लीनियर स्पेस और उसके डुअल में. क्यों नहीं दिखा रहा है? नहीं, इसको क्या प्रॉब्लम हो गई है? अच्छा ठीक है, अब ठीक है. सो हमने किया था कुछ वीक कन्वर्जेंस के बारे में. तो एक तो है नॉर्म कन्वर्जेंस जो यूजुअल कन्वर्जेंस है. नॉर्म कन्वर्जेंस इन एक्स, इतना लिखा है. A normal linear space तो जिसमें हम कहते हैं कि xn converges to x in norm if and only if norm of xn minus x as a number, as a sequence of numbers goes to 0. And similarly जो हमने सब कुछ बताया, then हमने किया कि ओके, हमने किया था norm convergence implies weak convergence and weak convergence implies weak star convergence, है ना? So अभी हम हेड की इसको करें हम. हाँ, मैंने तुम्हें कहा था होम असाइनमेंट कर लो. वो चलो, होम असाइनमेंट तुम क्या करोगे? चलो उसको रहने देते हैं. होम असाइनमेंट तुम ये कर सकते हो, वीक स्टार कन्वर्जेंस does not imply a weak convergence. So let's take it as a home assignment, क्योंकि मैं अब कुछ आगे बढ़ना चाहता हूँ इसमें, और वो है हम करना चाहते हैं. Let's leave that. Okay. ओपन मैपिंग थ्योरम. ये है फंक्शनल एनालिसिस के बाद दूसरा इंपॉर्टेंट थ्योरम जो हमें करना है. फंक्शनल एनालिसिस मतलब इन जनरल फंक्शनल एनालिसिस का दूसरा बड़ा थ्योरम, ओपन मैपिंग थ्योरम. So it says that if x and y are Banach spaces, let me write down the statement. Banach spaces, Banach is important. यानी नॉर्मल लीनियर स्पेस अगर खाली हो तब ये, अगर ये कंप्लीट ना हो, नॉर्मल लीनियर स्पेस हो but not complete, then this theorem will not be true. If T is a continuous linear transformation, continuous linear transformation of f of x onto y, again onto is important, ये तो condition is important, then T is an open mapping. Then T is an open mapping. Open mapping का मतलब तो मैं ब्रैकेट में लिखूं, by that I mean if O is an open set X, then T of O is open in Y. Image of every open set is open under T. So चलो मैं अगर थोड़ा सा यहाँ लिखें, what is happening now, T is surjective यानी onto है map between Banach spaces that is linear and continuous. तो हम कह रहे हैं कि it need not be 1 1, मतलब surjective is important, it's onto, and T of X is the whole of Y. So then we say T is open map. It would send open sets to open sets. So इसका मतलब ये भी हुआ कि if in addition, अगर साथ में ये 1 1 भी हुआ, if in addition T is 1 to 1, then T is also a homeomorphism. तो इसका inverse भी continuous होगा. Inverse is T is a homeomorphism. Homeomorphism means एक ऐसा bijection जो continuous है और उसका inverse भी continuous है. यहाँ पर तो हो ही जाएगा क्योंकि ये subjective तो है. अगर ये 1 1 भी है, so T would be a bijection. और जब मैं कह रहा हूँ bijection is an open map, तो open map का मतलब क्या है? So T of E है ना? तो if A is open, है ना? If O is open, then T of O is open. तो उसका मतलब ये हुआ ना, if तो if कैसे मैं लिखूं? If G is open, या यूं लिख लो. I can write if, कैसे लिखें? यानी अगर ये bijection हुई तो inverse भी यानी T inverse of, let me write U is open. No, वही हुआ ना. नहीं, इसको लिख सकते हैं हम, अगर T O open है तो कैसे लिखें? If O is open in X, then T of O is open in Y. तो अब अगर ये bijection हुई in addition, अगर ये 1 1 भी हुई तो फिर it would be a homeomorphism, यानी T inverse भी continuous होगी. तो T inverse then would be a mapping from Y to X. So if O is open in X, then T inverse of O, which is equal to T of O, is open in Y. यानी उसका मतलब वो T inverse जो है वो continuous है ना. ओपन मैप का मतलब क्या है? अगर O open X में है तो T of O is open in Y, but T of O can be also written as T inverse का inverse, क्योंकि if T inverse is the inverse of T, then मतलब inverse of inverse is the function itself whenever it exists. So if O is open in X, then T inverse का inverse, which is equal to T of O, is open in Y, which means it's open map, which means that T inverse is continuous since it is a bijection that is continuous one way in any ways. By the assumption of the theorem, it's a continuous linear transformation. So therefore, T must be a homeomorphism. You know, it's the second part. Now, if this part is true, second part is obviously an obvious corollary, obvious observation. Now we do the proof. Now, for the proof of this theorem, we need a lemma. For the proof of this theorem, we need a lemma. और लेमा क्या है? लेमा में भी assumption सारे यही हैं. लेमा, let x and y be Banach spaces. फिर से यही है अपना system. X and y be Banach spaces. And T is a continuous linear transformation linear transformation of x onto y जो ना ऊपर है, then the image of each open sphere centered at the origin, centered at the origin, on the origin in x contains an open sphere centered at origin in y. मैं इसको जरा explain करता हूँ. Actually, once we prove that, it's easy. मतलब almost prove हो गया कि it is an open map. So, तो but we take it as a lemma. But proof of the lemma जो है, उससे proof of the theorem automatic है. अब मैं क्या लेमा क्या कह रहा है? लेमा कह रहा है if again t x and y are Banach spaces, they are complete normal linear spaces, and t is an onto map, and if t of x is equal to y, then अगर मैं लूँ s कोई भी ऐसा element मतलब open sphere centered at origin, so that would be this thing. This is an open sphere in x centered at the origin in the domain. अगर मैं इसका image लूँ, so this would be inside y, but we are saying that it would contain some s dash. By s dash I mean all y belonging to y such that norm of y is less than some r dash for some r positive. Of course यहाँ r positive है. And this is the open sphere centered at origin inside y. यानी अगर मैं इससे सोचूं ना R2 में, तो मैं कह रहा हूं अगर मैं इसकी इमेज लूंगा इस ओपन स्फीयर की, तो वो ऑफ कोर्स क्योंकि लीनियर मैप की क्वालिटी है कि ओरिजिन वुड गो टू ओरिजिन, बट वी आर सीइंग दैट ये जो इसकी इमेज होगी ना यहाँ पे, इट वुड कंटेन सम, मतलब ये जो ओरिजिन है ये बाउंड्री पे नहीं होगा, ये इनसाइड होगा. द इमेज ऑफ दिस टी जब वो जो ओपन सेट होगा ना, मतलब इट वुड कंटेन some ball around origin. इसकी जो image है, image of the ball in the domain would contain some ball that's in the range. So that's the lemma. लेकिन इसको प्रूव करने के लिए हमें थोड़ी सी मेहनत करनी होगी. So let me call SR को मैं थोड़ा notation लेता हूँ. SR is all x such that norm x is less than R, where R is some positive number, and S dash R जैसा कि मैंने लिखा था यहाँ पे is all y belonging to y such that norm of y is less than R. ठीक है? R could be some positive number. And this is an open sphere centered in x, centered at origin in x, and this is an open sphere centered at origin in y. Let these be the open spheres with radius R centered at origin in x and y respectively. So we have to show that. Then I can write T of SR को मैं लिख सकता हूँ T of R into S1, which can be written as R into T of S1. इसकी जो मतलब they are the same because of linearity of T. तो अगर मैं इसको प्रूव करना चाहूँ तुम्हारे लिए, so I would take the eraser first and delete it. Yeah, देखो अब पहले तो मुझे SR is the same set as R times S1. So what is SR? SR is of course SR किसके बराबर है? all x belonging to x such that norm of x is strictly less than r, and r into Sn hoga, it would be r into x such that norm of x is less than 1. Can you see that it is the same set? Now suppose, चलो मैं लिख देता हूँ, suppose x belongs to SR, है ना? It implies that norm of x is less than R. वही है मतलब, which would imply that norm of x by R is strictly less than 1, which means that x by R जो है वो belong करेगा S1 में. S1 का मतलब all x belonging to x such that norm x is less than 1. So which would imply that R times x would belong to R times S1. So अगर x SR में है तो R times S1 में है. Of course ये रिवर्स में भी जाएगा. इसका मतलब ये दोनों सेट सेम है. मतलब सेम आर्गुमेंट थोड़ा सा चेंज कर. Nevertheless ये सेम है और of course t of Rx is always equal to R times t of x. So this would imply this because t is linear for any scalar, in particular for this R positive. So it is sufficient, इसका मतलब ये है, so it is sufficient to show that T of S1 contains some SR dash. यानी इसका मतलब अगर मैं दिखा दूं SR dash जो है is contained in T of S1, then it would imply I just have to, so which would be contained in R times T of S1. Okay, sorry. ये मैं जरा ड्रॉप करता हूँ, मैंने क्लिक किया. So it would imply that it would imply that R into SR dash is contained in R times T of S1, which is the same as T of SR. So which is the same thing as R dash is contained in T of SR. So since R is positive, R dash is positive, तो मैं इसको लिख सकता हूँ. मतलब सिर्फ यहाँ ये radius बदलेगा. I would have found that it contains a sphere centered at the origin with radius R into R dash. अब ये इसके बराबर है, ये तुम कर सकते हो. So अगर मैंने दिखा दिया this property by this observation यहाँ पे, it is sufficient to show that SR dash is contained in T of unit ball, in a ball of radius 1. तो हम दिखा सकते हैं, मतलब for any ball basically. अगर हमने radius 1 के लिए दिखा दिया, image of radius 1 contains a ball centered at origin in the range. Okay, so let's, तो हम अब इस पे फोकस करेंगे कि हम ये ऐसा है. We will show that SR dash is contained in T of S1 for some number here. तो ये हमारा पहला स्टेप था. नेक्स्ट स्टेप हमारा ये होगा, we first show, पहले हम दिखाएंगे ये that the closure of TS, अगर मैं इस सेट को लूं along with its limit points in Y, this contains some S dash R. ये पहला मेरा स्टेप है, तो ये हम पहले दिखाएंगे, पहला स्टेप. Now since T is onto, अब हम यूज करेंगे T is surjective. तो कहने का मतलब मैं कह चुका हूं पहले, T is a bounded linear map from X to Y that's onto, and X and Y are both Banach spaces. ठीक है. और A2 is, अब T चूंकि onto है, then Y can be written as union n runs from 1 to infinity T applied to Sn. So because Sn का मतलब क्या है? Sn का मतलब है ऐसे सभी x belong to x such that norm of x is less than equal to n. तो मैं क्या कर रहा हूँ, मैं कह रहा हूँ सभी वेक्टर्स लूंगा x के, तो पहले मैं लूंगा सभी जो S1 में क्या आएंगे, ऐसे सभी वेक्टर्स जिनका नॉर्म है लेस देन इक्वल टू 1। फिर S2 में लूंगा ऐसे सभी वेक्टर्स, ठीक है ना, such that norm of x is less than equal to 2। इस तरह से मैं सारे करके, तो अगर मैं इन सब का यूनियन लूंगा आई शुड गेट द होल ऑफ x, क्योंकि कोई भी नॉर्म जो होगा वो किसी न किसी नेचुरल नंबर से तो कम होगा ही। और अगर मैं सारे नेचुरल नंबर्स पे लूंगा, बिकॉज नॉर्मल्स आर रियल नंबर्स, तो रियल नंबर्स कैन बी पुट इनसाइड, look every real number is less than some natural number, and from that you can get t of x जो कि बराबर है y के should be t of this thing, and that would be union of n terms from 1 to infinity t of s. अब t y is a union of countably many sets. Now since y is complete, अगर तुमने पढ़ा होगा, वैसे पढ़ा होगा, Bayes category theorem says, by Bayes category theorem, y cannot be written as a countable union because y is complete of nowhere dense sets. इसका मतलब ये है, ये सारे के सारे नोवेयर डेंस नहीं हो सकते, तो देयरफॉर कम से कम ऐसा होगा इसमें जो नोवेयर डेंस नहीं है, यानी जिसका क्लोजर जो है वो उसके अंदर कोई इंटीरियर पॉइंट है, यानी जिसका क्लोजर कोई क्या बोलते हैं बॉल कंटेन करेगा सेंटर्ड एट सम पॉइंट of that set. So there exists some, therefore there exists some n naught belonging to the set of natural numbers such that this s sub n naught, t of s sub n naught का जो closure है contains some interior point, contains some interior point. Interior point means, and it contains some point such that s r at x naught या t of x naught के लेना चाहिए, s r of t of x naught is contained in t s n naught for some x naught belonging to x. But this should be true because of Bayes category theorem. Now which we may assume belongs to t of s n naught, क्योंकि मतलब इंटीरियर पॉइंट है तो इट मस्ट कंटेन, अगर ये बाउंड्री पे होगा, अगर ये लिमिट पॉइंट होगा, तो इट नीड नॉट कंटेन एन ओपन बॉल सेंटर्ड एट सम पॉइंट ऑफ इट। मतलब ऐसा जरूरी नहीं है कि फिर मतलब अगर बाउंड्री लिमिट पॉइंट है वो इंटरसेक्ट तो करता है टी एस एन नॉट को, लेकिन वो पूरी की पूरी बॉल हो उसके अंदर, ये जरूरी नहीं है। तो इसलिए हम ये मान के चल सकते हैं कि इट लाइज इन द टी एफ नॉट इन द क्लोजर, इसमें बिलोंग करता है। चलो इसका नाम रखते हैं कुछ, से let's call it y naught. So I am assuming that is y naught belongs to tsn naught. Now since y goes to y minus y naught, I hope that's clear, is a high homeomorphism. In fact, it's an isometry more than homeomorphism. Of y onto itself. itself. For homeomorphism sends open sets to open sets, therefore interior points to interior points. So I can say TS and not का जो closure minus y naught है has origin as an interior point. Interior point. क्योंकि इसका interior point है तो इसका इंटीरियर पॉइंट है तो ऑफ कोर्स अंडर दिस मैपिंग मेरे कहने का मतलब है अगर मैं डिफाइन करूं कोई मैपिंग f from y to y by f of y is equal to y minus y naught, it would send y naught to 0. And this is a homeomorphism. In fact, this is an isometry because f of y minus f of x जो होगा, this would be norm of y minus y naught minus x naught. That is just equal to norm of y minus x. So it's an isometry, it preserves length. So it is in a homeomorphism, it would send open sets to open sets, therefore interior points to interior points. But it would send y point, अगर अब y naught जो है, मेरे पास open set है नहीं, ये set है ts bar y naught minus this thing, and this minus, tsn sub naught minus y naught under this map. चूंकि इसमें 0 था तो ये जो ये सेट है इसमें origin होगा, पहले तो origin होगा, और चूंकि origin goes to this point from y naught goes to the origin under this map, so y naught was the interior point of the Sn naught, so therefore 0 would be an interior point of 0 would be an interior point of t Sn naught minus y, of course closure यहाँ पे, ठीक है. Now since I have also assumed that y naught belongs to tsn naught, we have, using the linearity of t, that tsn naught minus y naught, rather the homeomorphism, would lie inside. This can be easily checked. Actually, if something lies here, it must belong to S2n naught. Hence, T Sn naught the closure minus y naught would be equal to, oh, we are running out of time, T Sn naught minus y naught का whole closure. erase करता हूँ, confusion हो सकता है यहाँ पर भी. As a set, because it's a homeomorphism, it would send closure to the, closures would be equal. Closure of a set, if F is a homeomorphism in a metric space, yeah, topological space, if F is a homeomorphism, then F of A closure would be equal to F of A का whole closure. तुम्हें सिर्फ ये सोचना है, तुम्हारी मैपिंग जो है वो ये है. तो under this you have got F of A closure, अगर मैं इसमें, because it's a homeomorphism, is equal to F of A closure. So means F of A का whole closure किसके बराबर होगा? It will be y minus y enclosure. तो अगर मैं set लेता हूँ A की जगह Sn naught, T of Sn naught अगर मैं A लेता हूँ, so it means that F of Sn naught whole closure is equal to F of A closure. अब simply तुम्हें, sorry, ये थोड़ा सा लंबा चौड़ा प्रूफ है, हमारे पास टाइम थोड़ा कम है. What should I write? यहाँ पे गलत कर दिया मैंने. So by using this for this A, it would mean that F of T of Sn naught, the whole closure is equal to F of T of Sn naught का closure. So which would imply whole closure, apply the formula, So it is T of S and naught minus Y naught का whole closure is equal to T of S and naught closure minus Y naught. मतलब वही मैंने यहाँ लिख दिया. So let's leave it there. This is because this translation by a vector is a homeomorphism in a normal linear space. Okay, once I'm done, so this thing, but this would be if A is a subset of B, then A closure is a subset of B closure. So it would be T S2 and naught ka closure. Okay, hence I can say origin is an interior point. क्योंकि इसका interior point है और वो इसका subset है. So therefore it is an interior point of T S sub 2 and naught ka closure. Now since again multiplying by a non-zero scalar is again a homeomorphism. It's a homeomorphism of Y onto itself. I can just write, so I can write T of S2 sub and naught ka closure. It can be written as twice and naught into T of S1, which can be written as 2 and naught into T of S1 ka closure. So therefore, it follows that origin is an interior point of T of S1 closure, जो मैं चाहता था, which implies that, so I can see S dash epsilon, that is a ball centered at the origin of radius epsilon, would be contained in T of S1 for some epsilon positive. So, okay, पहला हिस्सा हमारा हो गया. We conclude the proof by showing that S dash epsilon is contained in T of S3, which is equivalent to इससे पहले मैं बता चुका हूं क्यों, that S dash epsilon by 3 is contained in T of S1. So once I'm done, so I have found an open ball centered at origin contained in the image of the unit ball, which means that for any image of any open ball into this map would contain some open ball centered at the origin. Okay, so let's show this. तो अगर हमने ये किया तो we are done. अब उसके लिए हमें थोड़ा सा मेहनत करना है. So let y be a vector in y such that norm of y is less than epsilon. यानी मैं कह रहा हूँ मान लो y इस जगह पे है, ठीक है ना, तो मुझे दिखाना है it would be contained in T of S3, है ना. तो यानी मुझे दिखाना है अगर मुझे ये दिखाना है, so therefore I have to show that there exists some x belonging to S3 with norm of a mod of T of x equal to y, है ना. And of course S3 का मतलब है x वो x होगा such that norm of x is less than 3. So that's what we are going to do. Now since now we already know that we have shown S epsilon जो है S dash epsilon जो है, it is contained in T of S1 का closure. This much we have already done, है ना. So okay, let's do it. Now since y belongs to, अगर यहाँ पे है तो this we have already shown it belongs to TS1 closure. अब closure में अगर कोई element है, then any ball centered at that vector would intersect T of S1. कहने का मतलब then I can say then there exists some y belonging to T of S1 such that norm of y minus y1 जो है, मैंने y लिखा यहाँ पे, y तो already है, y1 belongs to T of S1 closure, T of S1 such that norm of y1 is less than epsilon by 2, where of course that is there exists an x belonging to S1 with y1 equal to T of x1 such that ये जो y है, norm of y minus y1 is less than epsilon by 2. ठीक है, now we observe, इसका मतलब ये हो गया, now we observe that, ये ध्यान में रखने वाली बात है, if I take s dash epsilon by 2, it means that s dash epsilon by 2 is contained in T of S1 by 2. अगर मैं रेडियस को आधा कर दूं तो ये जो बॉल है ये कंटेन होगी. Why? What? That's rather, देखो कैसे. अब ये less than है epsilon by 2. I have got y1 is equal to some tx1, right? And y belongs to here. Y belongs here. So I've got this is less than epsilon by 2. Again, that would be, मैंने क्या लिखा है यहाँ पे? अगर ये इसमें बिलोंग करता है तो ये इसमें बिलोंग करता है because scalar multiplication would send closure to closure and interior to interior, right? So because this is just scaling down the vectors and that's a homeomorphism. So okay, so this is what we'd have. So then by the same reasoning there would exist a vector, there exists some y2 belonging to T of S1 by 2 such that I can go on and on this vector, because this vector does belong to S1 by 2. तो इसके और इसके दरमियान जो है I can find an open ball centered at this which would